Okay, my name is Bill Buchanan, and I host a podcast series on the world leaders in cryptography. And I'm so happy to host a true world leader in Vinod Vinaykanathan. Hi, Vinod.
Hi, it's great to be here.
Yeah, I hope I pronounced your
Oh, yeah,
surname
that's all
here.
right. I mean, I
Yeah.
would I go by my first name anyway.
Okay,
And yeah, yeah.
that's great. So Vinod is a professor of computer science at MIT and a principal investigator in the IT Computer Science and AI lab. He completed his bachelor's degree in the Indian Institute of Technology, Madras, in 2003, and his PhD in 2009 from MIT. His main supervisor was the mighty Shafi Goldwasser. Vinod is seen as a world leader in the area of cryptography, especially within the area of fully homomorphic encryption. He has co-authored many classic papers and which are seen as the third generation of homomorphic encryption, including trapdoors in hard lattices and new cryptographic constructions, and fully homomorphic encryption over integers. In 2022, he was the co-recipient of the Godel Prize. Vinod is also a co-founder and chief cryptographer at Duality Technologies. So what's your current role and what does a typical day involve for you?
For My day job is as a professor at MIT. I advise students. I teach classes. I spend a lot of time, working with students one-on-one on problems. And these days, those problems range from the core of cryptography, theoretical cryptography, to sort of the interactions of cryptography with quantum computing on the one hand, and also sort of security problems that come up in machine learning and statistics, and how cryptography can address those.
And so what's it like being in an institution that really invented public key encryption and almost has built the foundation? I know that in 1976 it was Whitfield Diffie and Marty Hellman on the other side of the
Right.
US at
That's right. That's
Stanford,
right.
but it
Drawn
was
and
really in 77 that we saw Reverse Shamir and
yeah,
Adelman
yeah.
produce RSA, which is still around after nearly 50 years. What's it
Correct.
like being in that environment and having so many amazing people around that built
Yeah.
such an
Um,
infrastructure?
so So I've been here both as a student, as a graduate student, like you mentioned, and later as a professor. And both times, all times, it is very inspiring as a place to be. The students here are extremely smart to and everybody is sort of smarter than me in some way, and that lets you actually continuously sort of learn from people. And if you have, I continue to have sort of problems that, some of which I can solve, some of which I can't, but that's what these great collaborators are here for. Yeah, this is a wonderful place to be, and a
Yeah,
wonderful place to teach as well.
yeah. So why Boston, Cambridge? Why not uh, uh, West Coast, California? Why did you choose uh,
Right,
MIT and choose to stay there?
right. MIT is home for me.
Mm.
Academically, that's where I sort of I feel like I grew up as an academic, as a researcher. So it was a very special place to return to. And the thought of kind of going to the West Coast didn't really occur to me. I did apply in one of the cycles, but eventually I wanted to be in Boston, really, either at
Mm.
MIT or at Harvard.
Yeah,
Um,
that's great. Yeah. And so, what were your school days like? So, obviously, you came to the US when you were older. What were you like at school?
um, yeah, I, um, um, I have a bit of an amnesia about about what happened before I was 15, but I think I was pretty curious about sciences. I loved chemistry when I was growing up. Mathematics was sort of there, I kind of enjoyed doing mathematical problems, but I thought I would become a chemist or something to do with sort of like a laboratory science. Uh, but then I went to compete in the Indian version of the chemistry Olympiad. And so what happened is you have a sort of a theoretical half of it and an experimental half of it. I did reasonably well in the theoretical half, but I completely botched up the experimental part. It had something to do with sort of nitric acid and handling it, and I'm not that great with my hands. So I ended up spilling it on the marble countertop, completely destroying it, and that disqualified me from the competition. So that, I think, around then I decided, you know what, theory is for me.
Yeah,
Um, Probably not the experimental sciences. And then when I did my undergrad at the IIT in Madras, I started working with wonderful professors there, and who introduced me to cryptography. And yeah, that stuck.
yeah. So what's generally been your track since then? So did you do the cryptography as your PhD subject?
Right, right. So I started sort of thinking and reading papers and sort of like studying cryptography from the time I was a sophomore at IIT Madras. Then that continued for a while, and I came to do a PhD at MIT, and that was really kind of the place to be to do cryptography. Um, so I did a mix of distributed computing and cryptography for my PhD. I worked on this problem called Byzantine agreement. So that sort of like was a sort of a pet problem of mine starting from my undergraduate years. And then I sort of moved on to sort of the rest of cryptography, and I started sort of thinking about lattices towards the end of my PhD. And that sort of, I've been thinking about lattices ever since. Um, so after my PhD, I went to IBM Research to do a postdoc for 2 years. And that was again a wonderful, wonderful place to be. Lots of names that one recognizes. Tal Rabin was
Mhm.
my advisor, supervisor at that
Yeah,
point. And Craig joined IBM in 2009, a year after I came there. Shia Levy was there, lots of wonderful people. Uh, and that's sort of when I got started thinking about homomorphic encryption. Um, then I spent a year at Microsoft Research, which is where I did my what I'm very proud of as my probably my most important work in FHE. And yeah, I just stayed there for a year and moved on to academia.
that's great. Yeah, so it's really nice the way that it's evolved from the end of your PhD. Sometimes the PhD is an end point,
Right.
but obviously
Really, it
that
was
was
starting.
something.
Yeah,
A
that's right.
starting point.
Yep.
Yeah, that's really. I think it was Leslie Lamport that created the Byzantine general problem, as I
That's right.
remember, and
That's right.
LaTeX and so many other things.
That's right. Exactly. Exactly. Yeah.
And what topics do you teach, and what's your favorite topic?
So I teach a mix of graduate and undergraduate classes. For undergraduate classes, I like teaching sort of algorithms. I am currently teaching a class on discrete mathematics for freshmen, for undergrads. I enjoy it. I also teach graduate classes. I continue teaching a class on cryptography, a graduate class on cryptography, and also advanced classes. I the last year, I taught a class on quantum cryptography. So this is really sort of the very fruitful intersection between sort of quantum algorithms and information and cryptography. So quantum information can both um, destroy cryptography thanks to, let's say, Shor's algorithm, uh, but it can also revitalize cryptography. It can enable cryptography with fewer assumptions,
Mm,
fewer unproven assumptions. It can enable things in cryptography like quantum money,
mhm.
which do not have any classical analog at all. So it can enable completely new capabilities. So it's a very fruitful sort of field, I think, and I really enjoy teaching that class.
Yeah, yeah. And I know there's things like one-shot signatures that can only happen within a quantum computer. So the
Exactly. Exactly.
and
That's
and
right.
and the concept of quantum. Could you just explain what quantum money would look like?
Yeah. So there's a range of these topics. Quantum money is one of them. Quantum one-shot signatures, like you mentioned, and quantum one-time programs is something that I've been interested in recently. So let me start with quantum money. Quantum information, cannot be copied in general. This is the no cloning theorem, the famous no cloning theorem of in quantum mechanics. Um, uh, and that sounds like a bit of a bummer if you're trying to build quantum memories. Because, like I do want to copy my information, for redundancy and for fault tolerance, right? And let's say I get a quantum email from you and I want to forward it to both, Shafi and Tal, let's say, right? I can't copy it. So that sounds like a bit of a problem. But um, but if you think about sort of the one thing in life that you really, really do not want copied, that's money, right? The government prints $100 bills, £100 bills, right? Um, with the infrastructure in place so that people cannot copy it at will, right? I mean, right now it's sort of accomplished using sort of like, special ink and special paper and so forth. But, quantum information just cannot be copied by the laws of physics, not by special ink or paper, right? So there's this idea that was due to Stephen Wiesner in the 1960s already, where he proposed how to use quantum information to create notes, bank notes. So quantum states become notes, right? And I give it to you, you can spend it, but you cannot double spend it. And that was really this came before the field of quantum information and certainly computation was a thing. So it was absolutely phenomenal as an idea. The paper had huge trouble getting published, and I think Wisner kind of gave up on it. And eventually he published it after Brassard and um,
Mhm.
Bennett and Brassard came up with their key exchange protocol. So this is sort of like a storied history around it. Um, the modern sort of research is about public key quantum money. What that means is Wisner's quantum money could be when I spend it, someone has to verify that this money is legitimate, and only the bank could do it in Wisner's proposal. So the merchant has to send the quantum state to the bank, who then verifies it. That's a bit of a problem, right? I mean, you don't want to kind of keep sending these states back to the bank, and the bank is a kind of like a central point of, as a bottleneck, really, right? Um, so what you would want is a way for anybody to be able to verify that a given banknote is valid without giving anybody the ability to copy it, right? And that's called public key quantum money. And there's lots of sort of really, really interesting sort of work around it. And clearly, like you said, this is not something that is classically imaginable at all, and sort of the more recent research has been sort of about copy protection of programs, which is sort of like, why just money? Why can't you sort of like create, uncopyable programs, right? I send you a program, you can run it, but you cannot make 100 copies and sell it to your friends, right?
Mhm.
Um, or quantum one-time programs, which is a different take on this phenomenon, which sort of says, like I want to send you a program, you can run it like 100 times, one time or 100 times, right? But no more than that. And that, one can imagine is sort of like useful in sort of like protecting sort of like digital rights um, and so forth. And this is something that some versions of it can be enabled using quantum information. So that's something I've been recently interested in.
That's great. So could you just give us a quick outline of how fully homomorphic encryption works?
Right. Yeah. So uh, it sounds magical, right? So what you want is kind of like an encryption scheme, which is like a locked box, right? I mean, encrypting information is like putting the data into the box, locking it, right? Only the person with this private key can open the box and see it. Now, what I want is a box which sort of has sort of a glove compartment attached to it, right? And anybody can actually manipulate the data inside the box without actually being able to open it up and looking at it. So it's sort of, you know, mathematically, if you think of encryption as a function f, right? F of x is like the encryption of x. And I give you f of x and I give you f of y, you should be able to compute f of x plus y without actually knowing x and y. You only know f of x and f of y. And that is the mathematical notion of a homomorphism or an additive homomorphism. And that's where the name kind of comes from. So I want a function f which is a homomorphism, but is also an encryption in the sense that it's hard to go back from f of x to x.
Yeah. And it
Um,
obviously involves these lattices that we create. Can you give us an idea how big these lattices are? Because we all think about 2D,
yeah,
3D, and when it gets to 4D and so on, then it becomes a bit difficult. Well, what's the size of these lattices?
right, right. So you can use lattices of any dimension to come up with the scheme of this form, but it wouldn't be secure. And the reason being that the security of these schemes, the encryption scheme, relies on the property that you cannot solve the closest vector problem, which is given a vector in space, find the closest lattice point to it. In 2D, 3D, 4D, in fact, any constant number of dimensions, you can actually solve it pretty quickly. That's why we have to go to much higher dimensions, dimensions of the order of 500 or 1,000 or even more. Um,
Yeah.
so the higher dimensions is for security.
Yeah. And obviously we have a point on the lattice, and then we add a little bit of error. And when we multiply these vectors together, the noise keeps increasing and kind of swamp the actual uh,
That's right. That's right.
data.
That's right, exactly. So lattices are additive structures to begin with, right? I mean, like if you add two lattice points, you get another lattice point. So it's not hard to imagine that a ciphertext, which is a noisy lattice point, can be added to another ciphertext, also a different noisy lattice point, to get yet another noisy lattice point. Now it's going to be a little bit more noisy than you started with, but still, a ciphertext. So addition seems very plausible, again, subject to the sort of the issue that the noise keeps growing. But multiplication seems very hard because a product of two lattice points, I'm not even sure how you would define it, is not a lattice point. I mean, that's not a guarantee you have, right? The first generation of homomorphic encryption schemes kind of dealt with it by working with a special class of lattices called ideal lattices, where multiplication of lattice points actually makes sense. Um, but what we sort of, you know, started thinking about with Zvika Prokarsky, this is where my FHE work comes up, um, is do you need this multiplicative structure? Do you need these like ideal lattices to actually make fully homomorphic encryption tick? And we realize that you don't. You can actually endow lattices with a type of multiplication, which comes from the tensor product, uh, and that can make homomorphic multiplication work as well. Now, in both these cases, the noise kind of increases over the course of time. Uh, and, you can set the parameters of the lattices, like the dimension and the distance between lattice points, to be correctly so that you can do a lot of additions and multiplications. But eventually you will run out of steam. And this is where Craig Gentry's bootstrapping theorem comes up. He gives a way to reset the noise periodically to some absolute threshold, right? A minimum threshold. So you do that when you realize that your noise is too big, and then you keep computing, and then you reset, and so on and so forth.
Yeah. But it's obviously a lengthy process. Is that still one of the key bottlenecks within inside homomorphic encryption? Every so often, you've got to clean it up and apply this bootstrapping.
That's right. That's right. Bootstrapping is uh, probably the biggest bottleneck in actually making homomorphic encryption practical. We've made great strides in many other aspects of efficiency. For example, you can encrypt data without blowing it up too much. You can do additions and multiplications, few as long as there are only a few of them, pretty efficiently. But if you really want to do general long computations, you do have to clean up, and that costs a hell of a lot.
And are there other ways that we can implement fully homomorphic encryption without using lattices?
Yeah, that's a great question. Something I've been thinking about for a while. So there is a way to do it, starting from an even more kind of magical object called indistinguishability obfuscation. It's a mouthful, program obfuscation, really. And program obfuscation has been constructed recently without resorting to lattices. So you can go this sort of like indirect route and get a fully homomorphic encryption scheme without relying on lattices. Uh, but that route is, you know, um, um, if fully homomorphic encryption is like driving a Toyota, this other lattice-based fully homomorphic encryption, right? This other way of doing fully homomorphic encryption would be like driving a bullock cart from the Stone Age, so it's much, much less efficient at this point, even though it doesn't require lattices. So these are really the only two ways I know to get fully homomorphic encryption. Uh, but if you want sort of other constructions of somewhat homomorphic encryption schemes, which is basically, you can do a few additions and multiplications, a reasonable number, but not everything, right? You can construct them from other assumptions. For example, there's a recent paper that I wrote with colleagues at MIT where you can use the learning parity with noise assumption and the Diffie-Hellman assumption, the classical Diffie-Hellman assumption, to construct a somewhat homomorphic encryption scheme. So I think the research we haven't heard the last word about constructions of FHE. I really strongly believe that there are more constructions out there. We just haven't been smart enough to discover them yet.
Okay. And obviously, the bottleneck just now is the performance issue. We're using generic processors that aren't really fit in handling these large prime numbers, large lattices. So, how do you think the speed up will happen over the next few years?
That's a great question. It has to come from both sort of better algorithms, better ways of bootstrapping, for example. And there are many sort of recent works that make progress on this question. For example, colleagues from Duality Technologies recently wrote a paper at Eurocrypt, which happened last week, I think. They have a better, faster way of bootstrapping, right? So that's sort of one way to make progress, algorithms. The second way to make progress is using custom hardware. Like use either like ASICs, like custom built hardware, or harness the power of GPUs and FPGAs to speed up these computations, using the fact that these computations are essentially like glorified polynomial multiplications or polynomial fast Fourier transforms, which these guys are pretty good at. That's another way to do it. The third frontier, I think, is just kind of, there is a fair bit of work on hardware for FHE. There's a fair bit of work on algorithms, like making bootstrapping faster. But what is, I think, missing is the connective tissue between sort of people who write programs in high-level languages like Rust or Python or whatever, um, and sort of compiling it down to a form that FHE can actually act on it. So this compilation question, in my opinion, hasn't received enough attention, nearly enough attention as it should. And that I think is a frontier for sort of really making these things move to practice. Of course, there is the theoretical question, but theory, who knows? Mathematics, who knows when you will come up with an entirely new FHE scheme,
Yeah.
and that could happen too.
So, obviously, with post-quantum cryptography, there were many methods that were analyzed. The isogenies looked good because we could still implement the Diffie-Hellman type key exchange, but most of the other methods were looking at key encapsulation. So we've got code-based, we've got hash-based, and so on. Did you always know that the lattice methods were going to be the winner because of the performance and the key sizes?
No, it wasn't obvious at all, actually, to me. Um, yeah, the the performance in terms of efficiency of like the run times of encryption, decryption, and so forth were always good. At least starting from the time when you know ring LWE kind of came to picture, that really kind of changed the game. In terms of efficiency, but the key sizes were always large, larger than what the elliptic curve Diffie-Hellman scheme would give us. So it wasn't obvious to me that that lattices were going to be the winner, but it looked pretty good. So what I guess happened with isogenies is that there still are isogeny-based crypto systems that are alive and kicking, and they seem good. It just happened that the one that was proposed for standardization, the side crypto system, was horribly broken. Just sort of pull out a rabbit from the Kani's theorem, it's a rabbit from the hat, and that's that. Um, Code-based crypto systems also look good, but I believe, hopefully I'm right on this one, that they are not as competitive, not as efficient as lattice-based crypto
Yeah,
systems.
they're slower. Yeah, yeah,
Yeah.
yeah. Obviously, Macaleese is very slow, and it's been around for a long time, so it's pretty
Right.
secure. But I think HQC was standardized as an
That's right.
alternative to
In
Kyber because
March.
we've got Kyber, Dilithium, and Falcon are the three lattice, and I think there's still a lattice one that's in round two of the additional signatures. So
Right.
this still like lattices, hopefully, but they're looking
Right.
for an alternative
Right.
overall. And the hash-based ones are obviously the best for digital signatures. They're rock solid, but the signature
Right.
sizes are are quite
Large.
big. 17K, I think, is
So
a yeah.
So I want to say one thing though, which is if you look at public key encryption as opposed to digital signatures, right, which is in my mind the harder job, they're really the only two games in town are either lattices or codes. Isogenies, the C side, which is still alive, but it isn't in the contention for standardization, and hash-based cryptography doesn't apply there. So it
Mm,
really it's lattices and codes.
yeah. But there is a slight weakness in MLKM, that's the Kyber one, in that we generate the encapsulated key. So we don't start off with our own seed value. We actually out pops a small, relatively small um, key size from it. So
Right.
obviously it will change the way that we pass our key because obviously we use Alice's public key to be able to then create the encapsulated key, which is the key inside it. So there are opportunities for backdoors in this type of method that we don't have within the Diffie-Hellman method. So it will rely a lot more integrity.
Hmm. I hadn't really thought about that, but in my mind, not specifically talking about ML Chem, where there is really a choice of the polynomial, the cyclotomic field, I guess, which is, you know, um, people chose it one way, maybe there is um, a different way to do it. But uh, the the only thing that is kind of up to the designer in lattice-based crypto systems is either the prime, the number, the modulus over which things work, um, and the dimension of the lattice, so the dimension of the learning with error secret, right? So this is unlike, uh, pseudo-random number generators, which were backdoor, sort of elliptic curve based ones, where there was a choice of the elliptic curve, which was up to the designer, and we didn't know how or why things were chosen that way. And you can imagine that some choices can lead to sort of faster algorithms for a certain class of people and not for the general public, and that's a backdoor, right? So for lattices, you know, um, there's in my mind there's less of an opportunity for to insert a backdoor because there isn't so much non-determinism in choosing the parameters. But yeah, it's an interesting question to think about.
Yeah. I suppose it's always the random. oracle that's the problem. If that isn't quite random and it's picked, then you have a problem. And it goes back to the NSA
Right,
backdoor in elliptic curve, the dual
right.
EC algorithm.
ECPRP, yeah, right.
Um,
Mm. Yeah.
and I know that you've been working with the OpenFHE library, and there are lots of new primitives being created. It's really great to see that secret shares and other things. But we've got a whole bag of tricks, especially in crypto pairing and attribute-based encryption that aren't quite there yet in terms of being created as a lattice form. So what do you think the gaps are just now in us taking these older primitives that we've been
Mhm.
using for 50 years and
Hmm.
scaling them into a lattice world?
Yeah, that's a great question. Um, so, um, so lattices actually attribute-based encryption is an interesting story. Before 2013, the only construction of attribute-based encryption we knew is for sort of policies that can be written as shallow formulas or shallow circuits. So there's a class of formulas that you could handle, but not sort of like general policies, like arbitrary policies. Um, and the only way we knew how to do it was using bilinear pairings. Really, that was the only game in town. So we, with a student back then of mine, Sergei Gorbunov, and a collaborator, Hotek, we came up with a different ABE scheme, which was based on lattices, and it actually created ABE schemes for general sort of circuit policies. So that sort of like, lattices to me, increased the computational capacity of any primitive that was out there. We had degree 2 homomorphic encryption from bilinear pairings. With lattices, you can do all homomorphic encryption. We had maybe degree 1 um, predicate encryption from bilinear pairings. We could do all circuits with lattices. But there are other dimensions where lattices don't seem to be as powerful as bilinear pairings. There's a notion of a functional encryption scheme. That we know how to do it from. We have known how to do it from bilinear pairings for a while, and it's been improved for years. We don't know how to do that from lattices. And if you could do it from lattices, you would get uh, program obfuscation scheme from lattices is one of the big open problems in theoretical cryptography. So there are, these sort of like gaps out there, and that's sort of maybe one of them. Uh, what else is out there that you can do from pairings? I think functional encryption is kind of like the frontier problem in this area. But you're right. So people have been looking at sort of like the techniques used to construct crypto systems with pairings, and can I kind of like simulate these mathematical processes with lattice-based techniques? Um, there's a sort of line of research that attempts to do it, and they've had some success. In fact, I think they've had quite a bit of success, uh, sort of creating lattice-inspired analogs of something called broadcast encryption is something that happened recently. Um, um, but these constructions are not based on the worst case hardness of lattice problems. They're based on sort of LWE-like assumptions, which do not have the worst case connection. So I think there's work along the lines of what you asked, porting bilinear schemes to lattices, but there's lots more work to be done.
Yeah. And obviously, a frontier is within machine learning. I think in the OpenFHE library, you can train on a non-homomorphic SVM support vector machine
Yeah.
network, export the model, and then you can apply homomorphic encryption, which is amazing that you could run in the cloud a homomorphic encryption engine, feed encrypted data of your blood pressure or so
Yeah.
on. It would process and get it back, and you can decrypt with a
Right.
private key. And I
Right.
think I may be wrong with this. I've not looked too much at this, but a neural network, it's possible to use back propagation to train the weightings of a neural network. I may be completely wrong, but that if we could do that, then obviously LLMs could be transformed, that we could be using
Yeah.
homomorphic citizen data to be able
Yeah.
to do some good science. So
Yeah.
that's a big frontier just now, and I know that
Huge.
OpenFHE is making a lot of advancements. We're certainly using the SVM model, and it's working very well. We can't see the difference. I know there was a Stanford experiment on a genome project, the large
Mhm.
one, that
Mhm.
noticed there was virtually no difference between the homomorphic
Yeah.
data using, I think it was SVM they were using.
Right.
So
Right.
hopefully that will advance because that will really help Gen AI in
Yeah.
its problems about using personal data.
Right. Mhm.
And
Yeah.
so what was the main contribution on the paper, the classic paper of trapdoors for hard lattices and new cryptographic constructions?
Hmm. Hmm. Yeah. Yeah. So this is a paper that I wrote when I was still a graduate student, and I was working with. I was doing a summer internship at the Stanford Research Institute with Chris Picott. Um, um, and so. So what was the kind of the state of affairs back then was, Oded Regev had come up with his 2005 paper defining the LWE problem, phenomenal, really groundbreaking sort of work. Um, um, but but sort of if you looked at lattice-based cryptography from 95, 96, when Mickey Aitai invented it, up to about 2007, I mean, the kind of things you could do with lattices, the kind of cryptographic primitives you could build from lattices, we knew how to build elsewhere. Public encryption scheme, well, thank you very much. We have Diffie-Hellman. Why do we need the new one? And um, so the systems we could build using lattices were less efficient typically than the ones you could build without lattices. So sort of like a theoretical curiosity, right? Like this whole lattice-based cryptography. So so what happened in sort of like 2008 to maybe about 2010, 2011 is we both figure out how to build much more efficient cryptography from lattices. So really taking it from theory to practice, but also cryptographic primitives that we couldn't build otherwise, like FHE, right? So that really kind of this sort of 3 or 4 years kind of took lattices from just sort of a curiosity to really now a standard, right? That's where the transformation came up. So the paper in particular, we looked at a signature proposal, digital signature proposal of I believe Goldreich, Goldwasser, and Halevi from the 90s. So they try to kind of use lattices to do digital signatures. And their idea was, the signature key is a public key is a lattice, is a basis for a lattice. And the private key is a short basis for the same lattice, a basis containing very, very short vectors. Um, and when they wanted to sign a message, they would map the message into a point in the space, in the real space, r to the power n. And the signature would be a closed lattice point. So the signing process would require you to solve the closest lattice point, the closed lattice vector problem, which you can do with the private key, the short basis, but not otherwise, right? So that was idea, wonderful idea, really. But the particular way they implemented this idea was broken in 2006 by Ored and Fong Nguyen, um, because they used a deterministic procedure to compute the closed lattice vector. So it turned out that that was kind of the bottleneck in their scheme. So what we said is let's take this wonderful idea and make the signature, make the signing algorithm randomized in a way that gives you provable security, that prevents leakage and gives you provable security. And that's why we came up, that's for that reason, we came up with this Gaussian sampling algorithm, which is a way to sample from a Gaussian distribution whose support is on the lattice. And that created the digital signature scheme, and we combined it with a trapdoor, lattice trapdoor of Mickey Aitai from the 90s to create an identity-based encryption scheme. That was a second contribution to the paper. But really, I think the enduring contribution is the Gaussian sampling algorithm, which is, if I understand correctly, it's incorporated into the Falcon signature scheme. It uses the
Yeah,
GPV sampling procedure.
yeah. I like the Falcon scheme. It's got much smaller key
Right.
sizes and than
Yeah.
dilithium, and it's obviously produces smaller signature sizes than Sphinx Plus. So it's a great, and it's a
That's right. Yeah.
purer lattice method than dilithium is. And so with integers, we convert them into ones and zeros into a binary form. With floating point, we have this horrible IEEE format where we try
Yeah.
and represent a floating point value. So how do you
Yeah.
represent integers and floating point values in a lattice?
Um, good. So, you can either encode your message, which is an integer or a floating point, into the lattice point itself, or you could encode it into the noise, into the bits of the noise, into the sort of the most significant bits of the noise. So there are really kind of like multiple ways of doing this encoding. If you want to encode it into the lattice as a lattice point, integers make the most sense, right? I mean, after all, a lattice point is a linear combination of the basis vectors with coefficients being the integers, so you can put your message there. Um, there are there's a sort of a yet a new we talked about the second and the third generation of homomorphic encryption briefly, but there's a fourth generation of homomorphic encryption from with a CKKS scheme that actually encrypts sort of uh, uh, real numbers, floating point numbers, and the way they do it is they encrypt it into the noise. Of course, you have to make sure that the noise doesn't completely clobber the message. So you have to put it a little bit, not really the least significant bits, a little bit further away. But that actually lets you do sort of fixed precision arithmetic. Floating point, I think, is a giant pain. It continues to be a giant pain.
Yeah. And when we've got strings and things like that, so how do we, because it only works on integer values, just like most of public key encryption, it's all comes down
That's
to
right.
integers. How do we deal with matching strings and so on?
That's right. So at the end of the day, I think you convert them to numbers. I mean, that's really that's really what one has to do. I don't know of a better way to do it. And in a sense, that is what actually makes, you know, seemingly easy problems like string matching difficult under the homomorphic encryption. So things like comparing a letter to another letter. It is not an arithmetic operation. It's not addition. It's not multiplication. It's I don't know comparisons, right? I mean, and that is not arithmetic enough for FHE to do really efficiently. So at the end of the day, you have to convert it into bits and then do like a bitwise circuit, or maybe higher order digits, but not too high. So these, like at the end of the day, comparisons are continue to be a bottleneck for FHE based computations.
Yeah, because I think in OpenFHE there are three main models. You have the BGV, BFV for
Yeah.
integers, you have the CKKS, and then you have these circuits. They're
Yes.
very
Yeah.
slow
Yeah.
indeed. But you could really build any logic as a
That's right.
circuit. And obviously
That's right.
that's a big barrier just now that these methods are still fairly slow. When I run them, I
Right.
can only use a toy circuit because I don't have a
Yeah.
GPU. Because
Yeah.
that's
So arithmetic is great.
mhm.
Comparisons and string matching, well, they are slower than you would think. But if I may, there is sort of creativity in taking the problem or the algorithm that you want to run and writing it in a format that requires as few comparisons as possible. Just to give an example, there's a question of searching images, right? I mean, if you do that sort of the naive kind of algorithm, you would need to run a circuit, really, right? Um, but what you could do, you know, colleagues at MIT came up with this idea. Um, you could use embeddings. You could use these semantic embeddings, right? So you embed an image into a vector space. So now they're numbers, an other image into a vector as well. And now similarity search becomes in a dot product of these two vectors, which is very FHE friendly. So there's creativity in kind of like rewriting computations so that they only involve FHE friendly primitives.
Yeah, I think Apple are doing a lot in that space just now. They are using encrypted searches because we used to use crypto pairings for that
Right.
kind of thing. So now we can use an XOR type function, determine if the value is zero and so on. So I think that circuit approach is really great for things like text searching. So 14 years ago, it's a long time, you published a paper on whether homomorphic encryption can be practical.
Mm.
What's your feelings now?
Um, Homomorphic encryption at this point cannot solve world peace. It cannot train, you know, uh, uh, um, Llama or
Mhm.
ChatGPT. Uh, but it can do interesting computations which you would like to do privately. Things like genome-wide association studies, computations, things like image similarity search, for example, which can be transformed into a product. Um, so what I think is, this is sort of like the technology hype cycle, right? I mean, you think, at some point in the hype cycle that this will solve everything in the world, right? But that isn't really the case yet, certainly yet. But there's a large class of computations that we that we can currently enable with FHE, uh, and I think really the question right now is one of finding the right applications. Like what are the killer applications of FHE? I think at this point it has to be sort of applications which use a limited amount of homomorphic computations. Um, but I think there are lots of applications which fall into this bucket.
And you're a co-creator of the OpenFHE library, which I and my team use greatly. Both C++ and Python. We
Yeah.
use obviously the Python version is a lot slower, but the
Yeah.
C++ is probably the best because Seal was created by Microsoft and they've not really done much with it. So what motivated the team to actually create this open source library?
So a large part of the work on OpenFHE was my co-authors, was done by my co-authors. Yuri Polikov is
Yeah.
probably the kind of the spearhead of the
Yeah.
project. So I think what we wanted to do was, to put out a set of libraries that incorporate the latest and greatest advances in FHE in a way that people can potentially sort of start using them and building applications with them. Um, all this kind of started from a DARPA project in 2011. DARPA sort of saw FHE. They said, "Oh, let's put some money. Let's give a bunch of people a bunch of money and try to kind of make it faster." And that really paid off really well, I think. I mean, if you look at sort of the ecosystem of startups and libraries and so forth, you can trace back to what happened. With the DARPA project. So the library, I think, the one that Kurt Roloff, he kind of kicked off this project. He started building, um, came from that time, and they sort of steadily added on features and algorithms and improvements, optimizations to it, and made the usability better as well over the course of time, I think. So I think the motivation was to kind of have this sort of one-stop shop if you want to sort of build FHE applications.
Is there any alternative libraries that researchers should be looking at, do you think?
I think there are a handful of those. I haven't been really keeping track of what the current status is. I mean, Seal used to be around, and even before that, actually, Shia Levy's HElib was a pioneer in
Yeah,
this field.
yeah,
But HElib, if I understand correctly, the efforts have sort of gotten merged with OpenFHE. Seal, I don't know if it's maintained anymore. So. So I'm sure there are other libraries out there, but OpenFHE is probably one of the, if not the leading candidate.
yeah. It's good. And you worked on multi-party computation with threshold, fully homomorphic encryption. Can you outline how that works?
Yeah, yeah. So the idea of threshold cryptography is, or rather threshold encryption is to sort of take your private key and split it into many parts so that to get fault tolerance, really, right? I mean, if somebody breaks into one, two, three, four of these computers, they will only get four shares and nothing about the secret key. So what we wanted to do was to actually endow homomorphic encryption with the threshold decryption capability. So can I now have n parties that each hold a share of the private key, which can take the homomorphically evaluated ciphertext or a fresh ciphertext, whatever, a ciphertext, and collectively decrypt it. So each party will compute a share of the decryption and they'll all get combined together to get the message. So that's what we did. We took the FHE scheme that I came up with Zvika Brakarsky in 2011, and we endowed it with the threshold decryption capability. So that was a 2012 paper, and I think people have been building on it and making it maybe more efficient, fewer rounds,
Yeah, we're still struggling with distributed key generation area.
Right.
Typically around the ECDSA, it's just a horrible signature method.
Right.
EDDSA is much better, but I think ECDSA, just the way it was created, just
Beats me why
is a
people
nightmare.
use it beats me why people use ECDSA. I mean, it's just a mathematically an extremely clunky
Yeah.
piece of I don't know.
Satoshi Nakamoto caused it. It was his
Oh,
problem. He selected
okay, okay.
ECDSA. And I
All
think
right.
they tried to avoid Schnorr's
Right.
patent.
Yeah.
So the natural thing for Bitcoin would have been an EDDSA type approach, the
Right.
non-interactive zero knowledge proof. But
Exactly.
because of the patent at the time, they couldn't use that. So they used the ECDSA, and now it's Ethereum,
Yeah.
an Ethereum virtual machine, and it's Bitcoin, and we can't avoid it. So it's quite horrible. But I think your methods have been integrated into the OpenFHE
Right.
library for this distributed signature
Yeah.
approach. And I
Yeah.
think there are so many great applications of that. So I've got a real blind spot when it comes to garbled circuits. I understand most areas of cryptography, but garbled circuits just lose me. And I do understand functional encryption and ABE, and I've talked to some of the real creators of that. Could you just outline how garbled circuits and functional encryption works, and what do you think the key application areas of these are?
Right. So garbled circuits were originally invented for two-party secure computation, right? And the idea there is I have a function and you have an input to the function, and you'd like to get f of x. I have f, you have x, you would like to get f of x. And sort of Andy Yao's idea was to kind of take this function written down as a Boolean circuit and write it in a form that hides what the circuit is doing. I'll send this circuit, this garbled circuit to you. You can compute it on your one input, right? And you get the output, but that's about it. It doesn't reveal any more information. So the way it works is sort of you take each gate of the circuit, look at its truth table, right? Let's say an AND gate. Um, and so like if the first input is zero and second input is zero, you get a zero, right? You want to write a different table, a cryptographic table, truth table of the AND gate, which has like keys in it. Instead of bits, it has keys in it. So zero and zero will be like basically two keys, two separate keys, one for the first wire and one for the second wire. And the third entry, it won't be a zero. So zero, 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 right? So the third entry won't be a zero. It'll be an encryption of the zero key of the output using both these zero keys. So think of it as an onion encryption. So take the zero key of the output, encrypt it with the zero key of the left wire, encrypt that with the zero key of the right wire. The effect is what is important. The mechanics is not so important. What the effect is important? The effect is that if during the computation of this garbled circuit, you somehow manage to get hold of the zero key, the left wire, and the zero key of the right wire, now you can suddenly decrypt this onion encryption and you can get the zero key of the output wire. So that kind of mimics the logic of the computation. So zero and zero becomes zero, right? And an analog of this logic is that if I have the zero key and I have the zero key here of the right wire, I get the zero key of the output wire. And so the idea is to kind of create this cryptographic uh, blob that mimics the logic of each gate, and in a way that these blobs can be put together. So having like a blob for the AND gate is not so interesting. I mean, thank you very much. That's not, we love the AND gate, but only when it's put together with other gates, right? Um, so we want a composable way of doing this. So we want these blobs to kind of feed into each other. And the way I described it, right, the inputs wires are keys, the output wires have keys. So you can put these things together, and the keys can kind of feed into each other and kind of go into the output. So I don't know how well, garbage circuits is one of the hardest things to teach in class for me. Um,
Yeah.
and it's really magical. But I think that at the end of the day, the point is to sort of take a logic and mimic it with cryptographic means.
Yeah. Yeah.
Um, yeah.
It's great. Yeah. And how does attribute-based encryption work, and what do you think the core use cases are?
Right, right. So in attribute-based encryption, right? I mean, when you encrypt data with the regular public encryption, you encrypt it to a recipient, right? I mean, to their public key. Uh, Instead, in attribute-based encryption, you want to encrypt it to a capability, really. You want to encrypt it to anybody who has a certain capability. For example, I could encrypt my email and have it be openable by anybody who has the right credentials, right? So what I would do is I would take my email, I would encrypt it, I would attach a metadata to it, right? And for example, the current date, the expiry date of this email, and the organization and so forth. And anybody who has the matching kind of key, the right organization, right, and they're reading it, they have the key for the right dates, right set of dates, they can actually open it and read it. So it's sort of like a multi-recipient encryption, if you will, right? I mean, many people can open it, and this who can open it and who cannot is determined by a policy. Uh, that's the idea. Where would it be applied? I mean, I can imagine applications in file systems where you encrypt files. You want to share files like Dropbox style, uh, but you want to share it not with particular people, but people who have capabilities. For example, I might want to share my, you know, um, my receipts with all the admins in my organization, right? So anybody in that role can open it up and process it. Um, so file systems are a natural application. Um, Kind of you know, using it in practice in the context of file systems, uh, is probably a bit of a challenge. In terms of kind of, already tagging files is a bit of a challenge. I don't know if anybody actually does it, although that might change with, you know, you know. I'm going to regret that I said it. AI models, which automatically tag, potentially files, right? I mean, then you could encrypt it with these tags as your metadata and keep going, right? So that comes across as a potential application down the line in the future. In fact, I wrote a paper with colleagues at MIT outlining this sort of system, an architecture of the system. I don't know anybody who's working on it to to transition it into practice, though.
And I know that ring signatures was created by Ron Rivest. I may be wrong with this, but he was one of the first to come up
He
with
must.
this group
He must.
signature approach a long time ago,
Yes.
1978, 79 or something like that. So what, how, can you outline how a group signature works within a lattice?
Hmm. 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 Um, so this has been a while ago, so I'll have to remember. Um, so maybe just the idea of a group signature, right? I mean, it's a sort of a way of um, you know, there's a group of n public keys, right? and I want to sort of generate a signature on behalf of this group.
Yeah.
So people who look at the signature shouldn't know that it was I that generated the signature, for example, right? So one way to kind of do this would be to use zero knowledge proofs in conjunction with regular digital signature schemes. So, I would generate a signature with my private key, right? But I wouldn't just release it because that wouldn't be anonymous. I would encrypt it and release it. But now, sort of before everybody could verify the signature, but they would know that it was me that generated it. Now nobody can verify the signature because it's encrypted. So the idea then is to sort of stick with the encrypted signature methodology, but also prove in zero knowledge that what's inside the encryption is an actual signature scheme, is an actual signature blob, right? So that is kind of a general approach to group signatures that I believe Mihir Bellare might have sort of come up with this idea, the general idea. But back then, when we were doing this work with Jonathan Cards, we didn't know how to construct a non-interactive zero knowledge proof from lattices. So we had to kind of work our way around it. We had to kind of use an NIZK proof system for a particular computation, which turned out to be exactly the signature verification computation. So it was kind of like a putting together the right pieces at the right time. Uh, right now, though, it's been more than 14 years, 15 years. We now know NIZK proof systems for general computations from lattices. So you can go back to Mihir Bellare's template and just kind of like instantiate.
That's amazing. And I think you're currently working in the area of quantum factoring. Can you just outline what that is?
Right, right, right. Yeah, so I guess the Shor's algorithm, right, which factors numbers with a quantum circuit, uh, um, and people have optimized Shor's algorithm, Shor circuit quite a bit, um, but um, but it's still relatively large. The size of the factoring circuit asymptotically is n squared, where n is the bit length of the numbers you're trying to factor. Um, uh, and and it sort of came as a bit of a surprise when Oded Regev, a couple of years ago, came up with a smaller circuit to factor numbers, and that smaller circuit used lattices. That was sort of the surprise was twofold, right? I mean, um, now, if you peer into short circuit, there are lattices sitting there. It's sort of hard to see because they're one-dimensional lattices. But Regev's algorithm really kind of like takes this, goes to the extreme. And his circuit sort of has size n to the 1.5, so smaller than Shor. But its space complexity, so the number of qubits that it used, was n to the 1.5 as well. So in contrast to Shor, which used n qubits. So it was sort of not better than Shor in both respects. It was smaller than Shor as a circuit size, but bigger in the sense of the space complexity. So what we did with the student, Sion Raghavan, is get the best of both worlds. We got a circuit that's as small as Regev, which used as few qubits as Shor. Uh, so that is sort of my first foray into quantum factoring. We have a new work which factors not the RSA numbers, but a large class of numbers in with linear size circuits, with like n, the smallest possible circuit essentially, and sublinear space. So you don't even have to have as many qubits as the number you're trying to factor. So I think we will see quantum factoring in the real world um, by 2040. And in fact, I have a running bet with colleagues on it. I call this the 2040 cubed bet, which is that by 2040, we'll have a quantum computer that can factor 2040-bit numbers. And my bet is $2040 on it. A lot of people have bet against me because it seems preposterous to say this, because right now we don't even have a quantum computer that can factor 65, So it seems like a preposterous thing to say, but I think it'll happen. We are seeing advances in building quantum computers, in quantum error correction, um, quantum algorithms for factoring and other things. And uh, yeah, I think we'll see that happen.
Yeah. And obviously one defense for RSA is to keep ramping up the modulus
Mm,
sized
mm,
4K, 8K, 16K. I think is it was it Dan Binney or Daniel J. Bernstein said that we
Right.
needed a terabyte RSA
Yeah.
key. I think
Yeah.
it
Yeah.
was tongue in cheek to a certain
Yeah.
extent with that
It
paper.
was a sort of a bit of a joke, I
Yeah,
thought,
one
but I
terabyte
don't know what
was
Dan,
crazy.
his intentions were. Um,
Yeah,
so uh, well, it'll be just way too inefficient compared to, all these lattice and code-based schemes. So nobody will seriously consider using it, I think.
yeah,
So yeah.
yeah. And so, what's oblivious defense with ML models?
Hmm. Right. So that's an entirely different topic, which I am interested in, which is the intersection of interface of cryptography with machine learning. Lots of sort of machine learning models are used sort of you know every day. It'll be used even more as time goes on, and you know lots of people who have data will want to train their models but won't have the capability in-house inside their organization to do it. So they would outsource the training. This is what happens with like storage at this point. I don't have like a, like a disk here, which stores all my emails. I store it out there in the cloud. Um, you know, um, so that'll happen. That is happening with training ML models, and that'll continue happening, I think. But that kind of is a bit of a risky process because the person who trains the model can potentially insert backdoors into the model. There are lots of other concerns with ML models, and this is sort of like one sort of example of a concern. Um, uh, and what we did in a work with Shafi and Orzamir and Mike Kim a couple of years before was to show that a way for a trainer to insert an undetectable backdoor in a machine learning model. So this is a backdoor where, I'm the malicious trainer. I'll insert a trainer model. I'll give it back to you. You can look at the model all you want, the weights and whatever, the architecture. You wouldn't know that anything fishy was going on, but I have a backdoor into the system. So I can actually manipulate the input-output behavior of the system. So that's a concern. It's a concern also because it's undetectable, right? Because you can do whatever you want. You can audit the model. You won't be able to find the existence of this backdoor. So that was a concern. And the question is, what do you do in the face of potentially the existence of these kind of undetectable vectors? So what we said is, uh, you know, uh, you know, the idea of this paper is that you can remove backdoors without having to detect them, and that's why oblivious in the title, right? And the analogy you should think about is washing your hands with soap, right? So your hands have germs or they don't have germs. You have no way of telling them unless you have a microscope, right? Um, but you will wash your hands anyway. And the point is, if there were germs, now they're gone. If there were no germs, well, they still continue being clean, right? So the point is, you can clean your hands without knowing the existence of germs, and therefore you can clean potentially a model out of backdoors without having to detect that there was a backdoor in the first place. So that was the idea, and the way you enable it is using a really classical idea of program checking or random self-reduction from complexity theory. This originated from, work of Blum, Rubenfeld, and Kanan, I think, in the 1990s. And we used that idea. We sort of, the ideas there worked over bits and over finite fields. We ported them to work over the rails, and we said, look, you can now obliviously clean a model. I can't hear you anymore. I'm not sure why.
That better?
Ah,
Yeah.
better, better. Yeah. Hmm?
Okay. So, what's well, we talked earlier about quantum one-time programs, and it's really difficult to understand what they would actually look like. So, do you have a simple explanation of what a
Mm.
one-time quantum program is?
Yeah, I can tell you what it does, and maybe a little bit about the mechanics of how it
Mm.
happens. So they're very much like one-shot signatures that you mentioned. So what I would like to do is I have a signature key, private key. I'd like to give you this token, this quantum state, right, which will allow you to sign one message of your choice. But that's it. Only one message, right? Um, so the way it kind of happens, the way it was kind of like achieved, was using this notion of conjugate basis measurements, right? So with a quantum state, you can either measure it in sort of like the rectilinear basis, the 0, 1 basis, or the what's called the Hadamard basis, right? And if you do measure it in this basis, it's going to collapse to either the x-axis or the y-axis, and sort of any information about sort of measuring it in the conjugate basis is completely lost, right? So if you measure it in one basis, you cannot measure it in the other basis and get the answer, right? So we wanted to make measuring in one basis like a signature of 0, um, and measuring it in the other basis like a signature of 1. The result you get is a signature of 1. So you can either get a signature of 0 or a signature of 1, but not both. So that was kind of the idea. This was not our idea. This already existed. There's one-shot signatures. And now the idea is, how do you kind of take this and generalize it out of signatures to programs, right? So here is an idea that one could start with. It doesn't quite work, but at least it's a motivating idea, right? So what I'm going to do is I'm going to take a program, put it inside an obfuscated box. I'm going to obfuscate it. But this program is not going to take inputs, just inputs and compute on it and so forth, right? It's going to take input bits together with their signatures. So it's going to take bit 1, bit 2, bit 3, bit 4 together with the signature of bit 0, bit 1, bit 2, bit 3, and bit 4, right? Um, Now, what are these signatures? These are the one-shot signatures, right? So I'd give you this obfuscated program that demands an input together with a signature, together with a token that can generate signatures. So now you can use a token to sign any inputs that you want, feed it into the obfuscated program, and it'll compute the output for you. But you're done with the signature. Like you can't use the token to generate one more signature, and that was that. So you can compute the program once, but no more than that. So that's the basic idea. It turns out that what I said exactly doesn't work uh, for quantum reasons, but it can be made to work for a certain class of programs. And that's what the quantum one-time programs work. So,
Yeah, it's great. And what's a snarg? So I know what a stark is and
yeah.
snarks and so on. What's a snarg and how does it work with
Yeah.
lattice methods?
So a snarg with a G came before both of these things,
Uh-huh.
both of these apparently more popular sort of creatures, right? A snarg is just like a snark with a K. It's in the sense that it's a short argument of correctness of a big computation. But it's not an argument of knowledge, which is a K snark. It's just an argument of yeah, that's it. It just proves correctness. Um, what is it used for? Yeah, so I don't quite think we have seen like the full power of snarks being used for applications at this point. So right now it's sort of confined to blockchains or cryptocurrencies, the applications. Um, but one potentially very interesting application, I think, is to actually show the provenance of data as prove the provenance of data as it moves along a computation chain. So let's say I have a piece of data, right? I have it signed by the creator of this data. Let's say it's a news article or a photo, right? I'd like to kind of like change the photo, like crop the photo out, um, do one of a set of valid transformations, and I'd like to kind of give you the photo or the article together with the proof that, you know what, this was actually a photo created by so and so, followed by a valid transformation that I applied, right? So as the data moves along the chain of ownership, it should come together with a proof that attests to its origin and the chain of computations that you went through. And snarks can actually help here. Because every time you have a computation that you do, you attach a snark that you did this correctly. Snark is short, so it's not going to blow up as the computation proceeds. Um, so I think it's really a potentially interesting technical tool to prove provenance of data and therefore to combat things like rampant misinformation. Of course, it is a technological tool. It has to be used correctly within the right social and technical context. But this is an interesting sort of point of application, I think.
Yeah. Great. And obviously, as a researcher, every researcher has to make the decision on their intellectual property and their invention as to whether they patent something or they
Yeah.
go ahead and they publish. Obviously, with the RSA patent, MIT protected it. There was a spin-out company. It was very successful. Eventually, being bought, I think, by Dell or someone
Yeah.
like that.
Yeah.
Whitfield Diffie and Marty Hellman patented their method, and it didn't quite get protected, and they didn't do quite as well. But the Klaus Peter Schnorr paper held back some of the areas. You have the Fiat Shamir method and so on. So, what's your opinions on patenting cryptographic methods? A good thing or a bad thing?
That's a really great question. Um, I have several patents myself, and I think it is a valid tool to use to protect your intellectual property, and I would sort of use it, I would continue using it. But if there comes a point where, you know, it is clear that having a patent is it stifles innovation, I I think one has to sort of reassign the patent or give it up or whatever. I haven't reached that point. I've never had to do that. Um, but I think the story of ECDSA or DSA and Schnorr's signature should serve as a cautionary tale, really. I mean, I
Yeah,
would much rather be using Schnorr signatures and like, working with them than DSA at this point.
yeah, yeah. I agree. Yeah. And so, what does the next decade look like in cryptography?
Oh, wow. That's a great question. It is. I think it'll be exciting. Cryptography has really innovated constantly by deriving its motivation from both theory and practice. New questions, new ways of formalizing these questions, and new tools have all kind of flown into cryptography, and it has contributed backwards in spades, really, to these fields. I think that'll continue happening. So we have to. So I think for that to happen, we have to be careful not to become too insular as a field. We shouldn't sort of like, be in a bubble where, oh, we do our things and then we continue making incremental improvements and so forth. Rather, we should be looking outside and seeing what problems are out there, what security problems are out there. Quantum computing comes to mind, machine learning comes to mind, uh, and really using our toolkit to define the core of these problems mathematically. And definitions are something that cryptography is very good with, has been very good with. Um, and sort of like using our adversarial thinking to come up with creative solutions. I mean, we are good at sort of thinking like an adversary, and that's sort of like the kind of like um, the one skill that cryptographers should have, right? I mean, um, uh, I think cryptography has a big role to play in securing AI models, in actually building up this field of quantum cryptography. But we have to be open. We have to sort of learn new things, new ways of doing things, um, and not be too stuck with the status quo.
Yeah. And if you could change one thing about your career, what would it have been?
Ah, boy, I I think I'm good where I am. Uh, Yeah, uh if at all there's one thing I would have liked to learn more mathematics when I had the chance. I did a little bit. My minor was in mathematics at MIT when I was doing my PhD. Um, but I feel like there's so many hammers out there that I could be using that I'm not aware of. So, if I could sort of connect my brain to a bit of a math chat GPT that processes huge amounts of mathematics, uh, I'd be happier.
Yeah, I think it's a problem in that the type of mathematics that we use isn't taught that much.
That's
I
right.
learned everything. I had to relearn everything about elliptic curves, but I used the handbook of cryptography for most of my learning. But when I talked to the authors of that, they realized that they didn't include any elliptic curve
Right.
cryptography in there. So I think there's a problem with some undergraduate programs and some MSCs that they're not teaching that type of maths, and it's so interesting, and it's a real shame because it could really help software engineers, developers, and system architects to really design their systems better.
Mhm.
Yeah. So my last question. Thanks so much for for uh, for answering all my questions. So, if you were a new researcher, brand new in the field, what problem would you probably address?
Right. So if I were coming into the field right now, I would be looking at the field of either I would be looking at quantum cryptography, the intersection of quantum computing and cryptography, um, or I would be looking at uh, security issues in AI and machine learning. These are, I think, two very fertile fields. Um, Lots of really interesting problems, and really the ability to be at a place at the intersection of two fields. I mean, so some of the best science happens at the intersection of two sort of disparate sort of lines of thinking and fields, and that's when people from neither field are people who are established in either field have the inertia to move into the other field and learn it. But as a new researcher, you're very well positioned to fresh mind, clean slate, well positioned to actually be at this intersection, identify new important problems, and do great science. So I would encourage people to you know work between fields, and for me that is quantum information on the one hand, machine learning, AI on the other hand.
That's great. Yeah. So I think we've spent 50 years really cutting our teeth m- using these methods that weren't quite right. And
Yeah.
now is probably day zero. Day zero is we're actually going to do things properly. We're going to define trusted systems. We're going to properly protect data and so on. So I think we're looking at a world of lattices, and the work that you've done really has been inspirational and really built that, selflessly built that foundation for the rest of us to really build on. So I really see this as a new dawn, a new era of doing things properly and not
Yeah.
using these old trapdoor methods that didn't
Hmm.
quite really work overall. So thank you so much for answering all my questions and for taking up your precious time. Just keep up the great work and hopefully speak to you soon. Thank you.
Thank you for having me. It was a great pleasure.